In the last class, we had talked about how to get the specific impulse for a rocket motor assuming a simple one-dimensional steady flow nozzle theory. Now, let us look at in this class what are the deviations from that one-dimensional steady flow theory that we had. Okay. Now, if you look at what we had assumed, we had assumed something, and we will see what is happening in the real case. Okay. Firstly, we had assumed that the flow was one-dimensional flow, right. So, but what happens in a real nozzle is either the flow is two-dimensional or three-dimensional depending on the nozzle geometry. If you have a rectangular cross section, then the flow could be three-dimensional, but if it is an axisymmetric geometry, it could be two-dimensional. Okay. What does this lead to? If the flow is two-dimensional or three-dimensional, how is it going to how is it going to be different from what we had derived in class? What is going to change? Huh? If you look at typically what happens in a nozzle, the nozzle is going to be something like this. Then if you look at the velocity vectors are going to be right. So, there is going to be a component in the x direction. Okay. There is going to be a component that is going to go wasted. If it is axisymmetric, they will cancel each other out because of symmetry, right. So, there is only one component of this in the x direction that we need to consider, but we had considered the whole thing to be the exit velocity. So, that will lead to something known as divergence loss. Now, the second assumption that we had made was that the flow was isentropic. Right, but in a real situation, the flow is going to be non-isentropic flow. Isentropic is reversible adiabatic. It will not even be adiabatic because there is going to be heat loss to the walls. and because there is a boundary layer that is there, the effects of the boundary layer will make the flow again non-isentropic, and jet separation and shocks are something that are going to make it again non-isentropic. So, this is going to be the second deviation. Now, let us look at the other assumptions that we had made. Now, we had made this assumption saying it is an ideal gas. Okay. We had said that it is something that is a gas that will follow PV is equal to RT. That is not going to be there, and there is going to be viscosity. So, the real flow will be viscous plus sometimes you will get multi component gas flow, and sometimes in solid rockets, especially with the composite propellant wherein it is aluminized, you will get something like a two-phase flow also at times. Okay. So, and lastly, we had assumed that in the ideal case it was assumed to be frozen flow with constant thermodynamic properties. Okay. Whereas in the real case there will be chemical reactions taking place in the nozzle. Okay. And therefore, the properties are varying through the nozzle. Okay. If you look at all the four of them, the first three of them are going to reduce the specific impulse that we had calculated with our one dimensional flow. Okay. The last one is going to, in a sense, contribute positively. All of them were a negative contribution. This is going to contribute positively, primarily because if you look at what is happening inside the nozzle, the pressure and temperature are decreasing. So, that will favor exothermic reactions, and therefore, you will get a slightly improved performance than what we had calculated. Okay. So, we will look at it in a little more detail in this class. Now, let us firstly pick up divergence laws. Now, we are going to make an assumption saying that the nozzle flow is optimally expanded, but that need not be the case. For this derivation is still valid even if the nozzle flow is not ideally expanded or optimally expanded, primarily because we can take out one term. So, if we assume optimally expanded flow, then we know that P exit is equal to P A, and therefore our thrust equation becomes F is equal to m dot U E. Okay. Now, what we are looking at is, if you look at this figure, we are trying to calculate what is the thrust in the x direction. We do not worry about what is happening in the y direction, because of axis symmetry they will cancel each other out. So, we are interested in calculating what is happening to thrust in the x direction. So, if we take the sum of all the forces in the x direction, I can write this as integral over the cross sectional area rho into u dot into n, where n is a unit vector, into u x, which is the velocity in the x direction, into dA, the surface area. Okay. Now, we will get into a little bit of trigonometry and try and derive this, but before we go there, if we look at this nozzle, okay, we could look at the flow that is coming out through this nozzle as something that is coming out from a point source somewhere here, right, coming out from a point source at some this thing, and we are only interested in that cone that is seen here. Okay. Now, let me call this radius from the point source as r. Okay. Then this half angle that we are looking at, let me call it as alpha. Fine. Then we need to integrate this equation. So, we need to determine what is this dA. Okay. To do that, this is UE, which will have a component in the y direction and in the x direction. Right. Now, if you look at what is the area that we need to consider, let this angle be phi, and we are interested in the small elemental area d phi. Now, if you look at it from the other direction, you will get something like this. Okay. This is the area that we are interested in, and if this entire radius is r and this is at angle phi, what is this component? R sin phi, right? So, this would be r sin phi, okay, and this elemental area would be dA, fine. So, now dA would be this is 2 pi r sin phi, right, into what? 2 pi r sin phi is the circumference into d phi, right, r d phi, r into this small angle, let me call this as d phi, okay. So, it will be 2 pi r sin phi, that is the circumference, into this area, that is nothing but r d phi, fine. And we know that the normal is u dot n, not a vector, u e u dot n is what we are looking for. This is nothing but u e, right, and the component in the x direction, what is that going to be? Sorry, this is the component in the x direction is nothing but u e cos phi, right. So, sorry, u dot n is u e, u x is u e cos phi, right. And what we need to do is integrate this. So, let us do that. F x is equal to integral 0 to alpha u, this u dot n becomes u e, and u x is nothing but u e cos phi, and into the elemental area dA, which is given by this. So, two pi r square sin phi d phi. So, we will get okay, yeah.
So, dA is the elemental area, which is the plane section. So, the normal to that one is denoted by n. Normal to dA is denoted by n vector.
Yes, normal, so you are looking at the normal, sorry, you are looking at, if you take this is a you have to integrate it over this area. So, normal to this will keep changing. right. So, now let us look at simplifying this. This would need a little bit of your trigonometry. You know that sin phi into cos phi is what? So, sin phi into cos phi, we will get fx is equal to integral rho u e square 2 pi r square into integral 0 to alpha. Okay. Sin phi into cos phi is sin 2 phi. So, sin 2 phi by 2 right. So, now if we integrate this, what do you get? Minus cos 2 phi by 4, okay, 0 to alpha. So, what is this? I can rewrite this as rho right. First term will be minus cos 2 this I will have to no this right fine. Now, cos 2 phi, we know that it is nothing but minus cos square phi plus sin square phi plus 1 divided by 4, fine. We would like to retain it in terms of cos phi. I will come to why we are doing that in a little moment. So, sin square phi, I can write it 1 minus cos square phi. So, I will get okay. This is nothing but I can take out 2 as a common factor. So, I will get okay. Now, if you see here, we have a term in terms of r, which we would not know. We would want to eliminate this. One way to eliminate it is to look at what is the mass flow rate through this, and then we will hopefully get a function in r which we can use to eliminate this. So, if you want to look at what is the mass flow rate, m dot is equal to again integral 0 to alpha dA, right. Now, dA we know is nothing but 2 pi r square sin phi d phi. So, we will use that. And u dot n is nothing but u e okay. So, we will get, if we integrate this, rho e 2 pi r square integral of sin phi d phi 0 to alpha. So, this would be minus cos phi, right, and so you will get 0 is 1 minus cos alpha is what you will get here. Okay. So, we have got two terms here, one is the thrust and one is the mass flow rate. Mass flow rate, if you can see, I have put it as a function of cos, which is why I wanted to retain this in terms of cos. Now, if you look at this, I can club these two and write my thrust in the x direction as f x is equal to you will have a u e term and 2 pi r square will go away. So, you will get m dot u e 1 plus okay. Now, if you remember, what we started with was f is equal to m dot u e. So, we have now got a multiplication of 1 plus cos alpha by 2. This term is also denoted as lambda. So, in a sense, ideal thrust is multiplied by a factor lambda, where lambda is equal to okay. So, sorry, 1 plus so what is the maximum value of lambda we can have? Alpha, cos alpha can at best be 1, right. So, the maximum value of lambda can only be 1, and in real cases it will be less than 1 depending on what is this angle alpha. Okay. Let us look at how it affects by plotting this. If we plot f by f ideal, versus alpha, if alpha is 0, then the ideal thrust will be equal to the or the actual thrust will be equal to the ideal thrust. So, this factor would be 1, but if alpha keeps on increasing, cos alpha reduces, and therefore, this factor lambda will be reducing. So, this is how the graph looks like, and you see that typically we tend to use something like a 15-degree alpha conical nozzle in the subsonic portion. So, that will mean there is already some loss to the thrust that we get. Okay. Now, how do we minimize this thrust loss? One way to look at it is make this angle, exit angle, very small, right. If we make this exit angle alpha small, or 0 is impossible, right. 0 would mean that you cannot have a supersonic portion at all. So, you need to have this angle as very small as possible. Now, if this angle is very small, then you need a very large length to get to the exit area that you want, right, which is also not going to work out, because if you have a very long length, then your vehicle length will increase, and therefore, that is again a problem. So, how do we do this is something that was thought about long back, and people came up with a concept known as bell nozzle. Okay. Now, if you look at this figure, what we are saying is you will get a component only in the x direction, right. If somehow we were to make the flow as parallel to the x axis as possible at the exit, then we will be able to recover a larger fraction of the ideal thrust, right. Then we will be able to restrict our loss to a smaller value, right. That is what is the idea of a bell nozzle. Suppose this were the axis, then you could have a nozzle like this instead of the conical nozzle, which would have been something like this. So, you see that if you want to get to the same exit area, your length of the conical nozzle will be much longer, and if you have a bell nozzle, you will shorten it. Essentially, what is done in the bell nozzle is we increase the angle after the throat, right. We make the flow go through turn through a very large angle after the throat, and then make it go as parallel to the x axis as possible. Okay. So, there are two angles here that we would be interested in, that is theta I and theta E. Theta I and theta E in a conical nozzle will be identical, right, will be the same, whereas here you have the option of having a different theta I and a theta E. Theta I will be typically very large, around 30 to 45 degrees, and theta E will be somewhere between 2 to 10 degrees, and in between you have a parabolic profile connecting these two. Okay. Now, this would mean that you would have a shorter nozzle, therefore, the nozzle weight will be smaller, and also your cooling, remember nozzle is exposed to high temperature gases, your cooling load will also come down, because you are now looking at a smaller area to cool the nozzle. You will be having a smaller area wherein you need to cool the nozzle. Now, if you were to calculate what is the length saving that we will get, we can look at this table. Let us say we have a conical 15 degree, then for different area ratios what is the length that we are going to get. This would be something like 8.07. This is normalized with respect to the throat radius. Okay. So, you will have a non-dimensional number here, it does not depend on what is the throat radius, you can multiply it by the throat radius and get this value. And the lambda would be 9. Okay. This lambda here would be constant. Now, if we take well nozzles are usually denoted as 80% or 60% of the conical nozzle. Okay. So, if you take an 80% bell nozzle, then the length would be 80% of the length of the other nozzle. So, it will be something like 6.45 okay, and the lambda would be depending on what is the theta I to theta E. Okay. Now, if you look at this, the lambda values here and here, they are comparable, and in some cases you will get a higher lambda here, but whereas the length is smaller than the other one. So, in a sense you have saved quite a bit on the length, which means you will have a reduced nozzle weight. Okay. So, that is the advantage with a bell nozzle. Bell nozzles are typically used only in the upper stages and not in the lower stages. We will come to why that is so in a little time. If you look at the ideal thrust to the actual thrust, okay, and if you please remember that if you have a rocket motor, this is going through the atmosphere and therefore the altitude will change, right. So, depending on what is the altitude, let us say you have a bell nozzle and a conical nozzle designed for some high altitude around 14 kilometers or so, then it will give its best performance there, and what happens to it at other altitudes is what is of interest to us, right. This is how a conical nozzle will be, and a bell nozzle Now, if you see this, the off design condition, this is the design condition, right. Off design condition is poor for the bell nozzle at lower altitudes. If it is designed for a higher altitude and if you use it at a lower altitude, the off design condition for a bell nozzle is poor compared to a conical nozzle. So, which is why we would typically not want to use a bell nozzle at lower altitudes. Also, if you look at the rocket motors that are typically used in the lower altitudes, these are usually solid motors, and the pressure in the combustion chamber not very large, this is around 70 or something, and you can expand it only to around 1 atmosphere or so. So, what you would do is you would have a conical nozzle, whereas if you look at high altitude motors, they can expand to vacuum, near vacuum conditions. So, there you would need a very large area ratio nozzle. Okay. So, there you will try to use a bell nozzle, and at lower altitudes you will use a conical nozzle. We will look at a little more in detail about why this happens in the next class. Okay. But this is about the first component, that is the difference between real and ideal conditions that we had assumed. Now, let us look at the non-isentropic factors. How do they contribute to the reduction in specific impulse? typically this comes in because of boundary layer effects. Okay. So, because of the boundary layer and heat loss, so you will have typically some 3 components: momentum loss, due to friction near the wall. The flow needs to go to rest at the wall, and therefore you will have a boundary layer in which you will lose some momentum because of the friction. Okay. Then you will have, if you look at a nozzle, if there is a boundary layer, then you could also assume it as something wherein the flow is displaced by a certain margin, right. So, that will reduce the mass flow. So, construction of the due to boundary layer displacement thickness, and lastly heat transfer to the wall. If you look at these 3, this will be very small, right. This is not a significant component, and this will be the highest component. Now, the constriction of the flow passage, if you look at a very large motor with a throat radius of 0.5 meters or something like that, then the boundary layer thickness is very small compared to that. You will not lose out too much, but in a very small motors this can be of significance. Remember, the equation for mass flow rate that we have derived in class, we have not taken into effect this while deriving the equation, that is PCAT by C star. It needs to be multiplied by a suitable coefficient of discharge when you are looking at a smaller motor. For a larger motor it does not affect too much, but for a smaller motor it does affect quite a bit. Okay. We will stop here, we will continue in the next class. Thank you.